So welcome back. So having understood the basic principles of motion of PUMA robot, now quickly let us fill up the DH form. Okay, and all this we have explained. Uh, now, you see, I need to fill up this form. Okay, so link 1. What is A1? Because 0 and 1 they are same, except theta 1 everything is 0. Now link 2. So Z1 was this, and then you see it has flipped in this direction to become Z2. This is actually Z2. So I am looking from here, I am looking from here. So this is clockwise, so minus 90 degree. Twist angle, and as you know, twist angle is the angle between two successive z axes. Here it is minus 90. So why minus 90 is clear. And then since 1 and 2 again, the origin is same, there is no other parameter, all vanishes except the shoulder movement, theta 2, which has also a range minus 225 degree to plus 45 degree. This is also given on the drawing. Okay, so all are in degree. Okay, then come back to 3, the elbow. Okay, so this is Z3. So the this is Z3, this is Z2. Okay, so the distance between them, they are parallel actually. So distance between them is actually A2. Okay, so this is A2, 431.8 millimeter. When these two axes are parallel, I can put the distance of the distance between them anywhere, which is common normal. I have, but because they will be same, right? So through Z axis, please remember this is Z2, this is Z3. They are parallel. Okay, and A2 is the distance between them, which is this. Okay, now to get D3, you see D3 is the distance between two x-axis, successive x-axis. So this is actually x2. This is x2 because x1 and x2 are same. Yes, so this is x2, x1 and x2. Okay, so this is x2 and this is x3. This is the elbow joint making motion about Z. So the distance between them is D3. D3 again is geometric parameter given by the designer, 149.09 millimeter. And theta 3, the elbow motion is constrained between minus 45 degree to 225 degree. Now coming to 4. Okay, so this is Z3 and this is Z4. So if I look from here, there is a twist, right? 90 degree, plus or minus clockwise, so it is minus. You see, this is minus. Okay, and then A3. A3 is tricky. You see, the Z3 is perpendicular. So A3 will be distance between two z-axis, Z3 and Z4. So Z3 perpendicular to the plane of this figure, and Z4, which is having a twist clockwise 90 degree. So is between them, the distance between them, and measured. Why it is minus? You see, minus 20.32 degree, 32 millimeter. Why it is minus? So this is A3 because you are measuring along x-axis. X3 is positive in this direction, so you are measuring in this direction. So that's why it is negative. Okay, negative A3. Okay, and then you see, come here. So and then what is D4? So D3 is fine. D4 is the distance between x3 and x4. Okay, so x3 is this axis. Okay, and Z4 is this, and x4 is this axis. So the distance between two successive x-axis is actually D. So this is D4. D4 is 433.07 millimeter, and theta 4, that is this, is constrained to move between minus 110 to 170 degree. Then come back to 5. So 4, 5 and 6, they are very tricky and very easy also to understand. So see, this is Z4, this is Z4, okay, Z4. And what is Z5? Perpendicular to the, actually you see here, so this is roll, pitch, so this is yaw actually Z4. So Z4, and this is yaw, and then pitch. Pitch is actually clockwise. I am looking from here clockwise. So this is yaw, and this is the pitch. So if I look from here, this is anti-clockwise, so vector will be in this direction. So Z5. So Z4 in this direction, Z5 looking from here is a counterclockwise, right? Counterclockwise, I am looking from here. Is it clear? That's why it is positive 90 degree. So far so good, very good. I think you have understood. Okay, then all other, because intersecting axis, the beauty, so all parameters are 0, and theta 5 is constant to move between minus 100 to plus 100. And you see, and then if this is Z5, this is, I am looking from here, this is counterclockwise, so this is the Z6 direction, Z6, okay. So Z5 to Z6, I am looking from here, this is clockwise or counterclockwise, looking from here, clockwise, so then this is clockwise direction, right? I am looking from here, so clockwise, Z5 and Z6, Z5 and Z6, Z5, okay, I think it is visible from here, minus clockwise, that's why minus 90 degree, and as usual all other parameters are 0. Understood, no? Clearly? Pitch and roll, okay. Okay, sure. So that's the, once you have filled up the form, this is the most important form, correctly you filled up, and then you are ready to, this is your generator matrix, okay. Now same old story, read this row, put all the values corresponding to these parameters here, and you get, when I equals to 1, you get this matrix, transformation matrix of link 1 with respect to 0, which is very easy. You just put these values here and you will get this. Similarly, come on here, take all the parameters from here, okay. We are keeping theta 2 because right now these are, it will be required afterwards, the range will be required afterwards, okay. And likewise you get this, from row 2 you get transformation matrix of 3 with respect to 2 from row 3, 4 with respect to 3 from row 4, 5 with respect to 4, okay, 5 with respect to 4, then 6 with respect to 5 from row 6. So from all this, okay, you read this and put this here and you get the individual matrices. Well, so 1, 2, 3, 4, 5, 6. So there are 6 giant, 6 degrees of freedom, 6 individual matrices, 4 cross 4 homogeneous coordinate transformation matrices we have deduced. Next, we'll have to solve the manipulator, right? And that means, you see, solve means we are talking about inverse kinematics. First, forward kinematics. Forward kinematics is actually very simple. You all the matrix you have now 6 with respect to 0 will be equals to 1, 1 with respect to 2, 2 with respect to 3, 3 with respect to 4, 4 with respect to 5, 5 with respect to 6. So all these matrices you have, if you just put them together, you get any motion in this frame 6, you can capture it with respect to ground. This is the model, we call this is the model of the manipulator, right? Now, you see, if I just do like this and put these matrices and then I try to multiply them, it will be a huge one, right? So, what we do? We apply divide and conquer principle, right? To simplify our computation. So, what we do? Step by step, you see, first concentrate on wrist, okay? So, and this simplification will be extremely useful for inverse kinematics solution. So, concentrate on 6, that means 4, 5 and 6, 4, 5, 4, 5, 6, they are embedded here, and I have 5 with respect to 4, 6 with respect to 5. So, if I just multiply them, I get 6 with respect to 4, which is cos theta 5, cos theta 6, cos theta 5, sin theta 6 minus sin theta 5, 0. This is first row. Okay. So, I am writing, as you know, cos theta equals to cosine theta, sin theta equal to sin theta. But in our textbook, Craig has written also like this, only C for cos theta. So, as you wish, you can do that. Okay. C5, I thought C5 better to understand C theta 5 or C, theta I in that sense, right? Okay. So, we have used only the difference here with our textbook. So, this why we have selected this, because you see computation is easy and we have got this matrix which is giving you transformation matrix of 6 with respect to 4. Then again we have rewritten for your convenience, just copy all these 6 matrices, fundamental matrices, okay? And first step here we have got, this is we have got. Second step is actually we are coming after getting the transformation matrix from here, we are going one step up, okay? We would like to now calculate 6 with respect to 3. 3 is my elbow, elbow. So, that is nothing but 6 with respect to 4 and 4 with respect to 3. And here we already have. So, this one I write, and transformation matrix of 4 with respect to 3 I select from here. So, it is a multiplication between this matrix and this matrix, which will yield you this big matrix. So, with pen and paper, I suggest, you know, although every textbook it is there, in our textbook Craig's it is there, but if you take your pen and paper and once you do, starting from the scratch, that will give you enormous confidence and to tackle with any robot and design your own robot. So, that is why I suggest you please do it. So, I have got 6 with respect to 3. Third step is, you see, now up to here I am. So, third step is to go 3 to 1. Okay. Transformation matrix of 3 to 1 is nothing but multiplication of transformation matrix T with respect to 2 into 2 with respect to 1. Okay. So this already I have. I will borrow it from here. This already I have. I borrow it from here. So 2 matrix multiplication is doable. Okay. So if you do that and then you come across this matrix, it's not very ugly, isn't it? Huh? It's doable. Okay. And of course here cos theta 1 plus theta 2 equal to, you see, you will actually get cos theta 2, you see, you do it, cos theta 2 into cos theta 3 plus minus sin theta 2, sin theta 3. Okay. So this actually eventually give you cosine of theta 1, theta 3, theta 2 plus theta 3. Like that. This is again 12 class trigonometry. So this is the formula we use for this multiplication. You can do this multiplication like this. Like this. Then second, first row, second column will be like this. First row, third column will be like this. First row, fourth column will be like this. So in this way, you know how to do matrix multiplication, and you are doing it for so many years. Okay, so you do it and you get this. So very easy. Fourth step is from 2 you come. Fourth step is from 2 and 3 you get transformation matrix of 6 with respect to 1. Okay, just by doing transformation matrix 3 with respect to 1 multiplied by 6 with respect to 3. Okay, so 6 with respect to 3 you have got in the second step, and 3 with respect to 1 you have it here. 3 with respect to 1 you got it from third step. So from second and third step you can calculate this. Okay, so again it will be a little bit ugly. You will have to multiply this matrix, okay, and this matrix, whatever you can do, and then you see you will get this. And let us say that this is equals to R11, R12, R13, X, R21, R22, R23, Y, R31, R32, R33, Z, 0001. Okay. Say this is the final matrix. So each element will be, actually I am not doing it, you will get it from our textbook, or you can do it. Okay. But you see the rhythm. Okay. I just like you to see this. R11 cos theta 1 inside bracket cos theta 1 plus theta 2 times cos theta 4 theta 5 theta 6 minus sin theta 4 sin theta 6 bracket close minus sin theta 1 plus theta 2, okay, times sin theta 5 cos theta 6 bracket close plus sin theta 1 times bracket sin theta 4 cos theta 5 cos theta 6 plus cos theta 4 cos theta 6 bracket close. So this is your first element R11, right? By multiplying these two little bit ugly matrix, you will get this. Now if you just see the column wise, if I write R21 exactly the R11, just instead of cosine it is sine, and you see all this inside the curly bracket they are same. Okay, and outside the curly bracket it was plus sin theta 1, and in case of R11 or in case of R21 the sign got just changed to minus, and instead of sin theta 1 it is cos theta 1. Again inside bracket you see the term, the quantity, this quantity is same. So this is, in this way, analogy you can just, it will help you to remember. You don't need to remember, but this is good observation, because this matrix will be given. Okay, you do it in a relaxed way and you will be given always, you will be using it. And then R31 is equals to minus sine of theta 1 plus theta 2 plus theta 3 times bracket cos theta 4, cos theta 5, cos theta 6 minus sin theta 4, sin theta 6 bracket close minus cos theta 2 plus theta 3 bracket close sin theta 5 cos theta 6. Okay. So in this way you have got the first column. Okay. So in this way continued, you can see the second column you have written, and there is analogy. Very interesting, right? You just see the analogy, the similarities. Cos becomes sine, and all the term, all inside the curly bracket remain same as it is. Okay. And here again plus sine, it becomes minus cos. Plus sin theta 1 minus cos theta 1, and exactly the same. So this will help you actually. Okay, this is the case up to all the elements in the matrix, and then x, y, z is like this. Okay. Here also you see, here also you see x equals to cos theta 1 inside curly bracket, whatever you have. Okay. Y only sin theta 1, same thing whatever you have in the inside the curly bracket. Okay. Outside, of course, minus d3 sin theta 1 in case of x. In case of y, it is d3 plus d3 cos theta 1 plus d3 cos theta 1. And z equals to minus a3 sin theta 2 plus theta 3. So these are actually you are getting just by applying divide and conquer principle. Here I have given a reference that how it is different from is R32, R31, how it is different, and what is the similarity you can see. Okay. So that's it, and that's all the basic anatomy of PUMA. Now, having obtained all this, and you can meanwhile you can get this expression. This is the PUMA model. Okay, in any textbook, including our textbook, but you should do it. Then what next? You see, once I have got this R11, R12, R13, X, R21, R23, R23Y, blah blah. So you know 0, 0, 0, 1. This is equals to all these individual matrices. The good thing is they are function of only one parameter. You can check in the basic matrix which you have. So this is one, isn't it? You see, the basic matrix. This is a function of theta 1 only. This is a function of theta 2 only. This is a function of theta 3, theta 4, theta 5, theta 6. Okay. And one good thing about a robot is, you see, as you have seen DH parameters, all these parameters are fixed. Once the robot is given to you, they are not going to change. Do you think that twist angle is going to change ever? No. Do you think the distance between common normal is going to change? No, because it's a linked length. And BI, the distance between two common normal is going to change with the motion of the robot? No, never. Right? So what will change is only one parameter. So that's why in out of 4 parameters, DH parameter, 3 are called geometric parameters. So these are geometric parameters. And they will never change unless the design of the robot changes. And one is the motion parameter. And if it is a revolute, just like PUMA, then this will be the motion parameter. And if it is, say, revolute, and then prismatic, and then revolute, for prismatic joint, this will be the parameter which will vary, and this will be geometric parameter, this. Okay. So that is one simple thing, good thing. Now, once you have the model, that means the equations correctly, then I can even, you can take a task, um, assignment. Now these range values are very useful. What I want to do, I want to get a working envelope for the PUMA robot model. That means where PUMA robot can reach, that is called working envelope, where PUMA can work. How to get that? You see, you have all the parameter range, and if I run 6 loop, okay, nested loop. So this is first, second, third, fourth, fifth, sixth. So 6 joint has one, you see, 6 joint range will be minus 266 to plus 266. Okay, minus 266 to plus 266. Okay, so you, and then every joint has a 6. So this is 6, 5, 4, 3, 2, 1. So you can run 6 nested loop to collect all the data within the range and within the parameter which designer has given. You can really create the working envelope of the PUMA robot. Well, that's the take home from forward kinematic solution. This is called, when you see, when theta 1, theta 2, theta 3, theta 5, theta 4, theta 6, all these are given, and you are getting this pose. So running this nested for loop, you can get all the poses of PUMA, and those poses in a fused way you can think of, that is nothing but working envelope of the PUMA. Great. So this is all about PUMA anatomy to the context of solving, making a model and solving forward kinematics. Okay, and please do that, a good computer exercise. You have now all the information. Okay, you see the ranges are there. You can take these ranges, the values are there, D2, D3, all. So just you need, and for our students that is great, need to run 6 nested loop to get the pose. Okay, these are the references. Okay, with this, stay safe, and if you listen this video and if you enjoy, then I'll be glad. And if you have any comments, please come to the discussion forum, or you can just mail me or put your comment, constructive comment on this video. In the next video, we'll talk about how to solve inverse kinematics of PUMA, and then we'll come to same thing for Bixter. Bye bye.